In this session, we're going to dig deeper into the DataFrame API. So far, we got a little bit of an intuition about what DataFrames are, how they fit into this whole Spark SQL thing, and, we saw how to create them. We saw that if we have a DataFrame, we can use SQL syntax and do SQL queries on them, which is pretty cool. But it doesn't just end there. DataFrames have their own APIs as well, in addition to being able to use just arbitrary SQL syntax on a DataFrame. In this session, we'll focus on that DataFrames API. In particular, we'll dig into the available DataFrame data types. We'll look at some of the basic operations that are available on DataFrames that you should know about, because it's not like RDDs. And finally, we'll look at how to do aggregations on DataFrames, because there's also a little bit of a different way to do that as well. Okay, DataFrames in a nutshell. Let's recap some of the key points to remember when using DataFrames. So the first point is that DataFrames can be thought of as just a relational API over Spark's RDDs. So you're running ultimately on top of RDDs, the same RDDs we learned about in previous sessions, but you have a nice relational API over them now. And the reason for this is because it's just sometimes more convenient to use a declarative relational API than it is to use functional APIs for analysis jobs. We saw this in the last example, in the last session, where we saw this nice little query where we were trying to select some information about some employees and then filter it and sort it, and it was done in almost no code at all, and it was extremely clear to read. It would have been a little bit more involved and a little bit less clear to read if we had done it with a functional API. The next key point to hold on to about DataFrames is that they're able to be aggressively optimized automatically. So Spark SQL takes many years of research in the database communities, and we can apply them in Spark now that we have some computations that are built up in sort of a relational way. We can apply these relational optimizations to get the same optimizations that people in the databases community have been enjoying for many years. And finally, one thing that you're really going to have to remember, maybe it won't bite us right in the beginning of this session, but it definitely will later, is that DataFrames are untyped. So the elements within DataFrames are rows, and they're not parameterized by some types. So the Scala compiler can't type check Spark SQL schemas in DataFrames. They're just opaque to the Scala compiler. There's all kinds of analysis done by Spark SQL, but the Scala compiler doesn't do any type checking. So they're effectively untyped. So as I've mentioned a few times now, Spark SQL's DataFrames operate on a restricted set of data types. This is in order to enable optimization opportunities, so we always know exactly what the data looks like. So here's a list of the basic data types in Spark SQL. So in this column we have the Scala type, so all of the types that we're used to already seeing in this course, and these are the types that SQL sees, and this is a description of each of the types. These are all pretty standard Scala types, or pretty standard primitive types. We have things like bytes, shorts, ints, longs. We have strings here at the bottom. Interestingly enough, there's timestamps and dates from Java. We have things like floats and doubles, big decimal. These are all pretty uncontroversial data types, but these are the data types that Spark SQL uses. These are the core data types that Spark SQL is built around. In addition to these basic data types, Spark SQL has a handful of complex data types available to use, such as arrays, maps, and, in this case classes, but structs. So these are complex data types that can contain basic data types or other complex data types themselves. So you can build up richer data types using these things, these arrays, maps, or in this case, structs. Since each of these data types are represented a little bit differently in Spark SQL because of their history in regular SQL, I'm going to run through each of them to show you sort of the main differences. And really the main difference has to do with this contains null thing here. So in this case, an array, for example, an array of string in SQL is an array type with a string type, which is its parameter, with this Boolean here. And in this case, this Boolean is this contains null thing, which is set to true if the elements in the array tuple, in the array type, can have null values. So if it's possible for this array to contain nulls, we're going to have this conditional set to true, otherwise it will be set to false. So there's always this additional piece of data hanging around here called contains null. So we have not just type information about the type contained in the array and the fact that it's an array at all, but we also have some knowledge about whether or not this thing can contain nulls. The next complex data type that we're going to look at is a map. Just like maps in Scala, maps have keys and values, and the SQL version of this has types that correspond to the keys and types that correspond to the values. So a map type contains a key type and a value type, as well as this Boolean here, which represents whether or not the value type can contain null. Okay, so it's similar to what we just saw on arrays, but this contains null thing refers to the value instead. So if whatever is in this value, so in this case a string, if this value can be null, then this is set to true. So we know the type, this is nullable, basically. And finally, struct. So structs are a little bit less rigid than arrays and maps. The struct type contains a list of possible fields of different types. So unlike arrays and maps, which were one type or two possible types, structs can be any arbitrary number of types, but you have to have something called a struct field, which contains a name for the field, the type of the field, and then again, this nullable value here. So you can build up more interesting data types this way, and this is how you can take, for example, something like a case class and map it to something that SQL can understand. So in this case, we'll be using case classes in Scala, but in SQL, the same case class would look like this. So if we have a case class person with a field name and a field age, the name is type string and the age is type int. This can be realized as a struct type in SQL with a list of fields. One field, so one struct field, has the name, it has the type string, and it's nullable, it's possible to be nulled. And again, another field which has type has name age, has type integer, and also is nullable. So this is how we could represent, for example, a person case class object here. So these are the data types that Spark SQL can operate on. This is pretty important because if for some reason your data type doesn't fit into one of these shapes, it can't be worked on in Spark SQL. So just to repeat, Spark SQL has a restricted set of possible types. Nothing fancy happening in these types. You have basic structs, basic arrays, basic maps, and then you have this list of effectively primitive types that I showed you on the previous slide. And every computation that we will be doing in Spark SQL has to be able to be represented by these sets of types. And just to show you that it's possible to arbitrarily nest these complex data types, here's an example where I've taken some Scala types here. So these are actually rather complex and nested. So I have a type called account, which contains a field called balance, and a field called employees, which is an array of employees. But employee is defined as another case class with these fields here, with primitive fields int, string, and finally there's another case class called project with a type string as a title, and then another array of these employee objects, and then a value of type account here. So this is a rather complex data type, this project thing here. So if I wanted to represent this project type, I could do it here, just like this, in SQL. It's super involved, it's difficult to read. But this is actually just a realization of this project type here, which contains accounts and employees types. So you can basically write this code and then expand it to be this, right? So this here is project, right? And I'm sorry about the wonky trues here. Something happened in the PDF reader, but these are all struct fields, and these true things are the nullable booleans. And you have things like arrays. You have things like more struct types within struct types, and then you have, of course, primitive types. So here's a struct field of type string type with the name, for example. So again, these things can be nested and built up to represent reasonably complex data types. And one important note, so this is actually going to come up again and again throughout Spark SQL. Spark SQL really requires a lot of imports. Throughout this and the next few sessions, I've tried to tell you everywhere where you might have to have some special import to use one of the things that I'm showing you, though if ever in doubt, have a look at the Spark docs. In this case, in order to use any of the data types, you need to import all of Spark SQL's types. So that can be done like this. So again, if you're ever going to use a Spark SQL data type, you actually need to explicitly import the types that Spark SQL operates on. Okay, so what sorts of operations are defined on DataFrames? So far, all I told you is that the DataFrames API is all about relational operations, a relational API. So said simply, the DataFrames API actually is quite similar looking to SQL. Example methods include select, where, limit, order by, group by, join. You might notice that this is quite different looking from RDDs that you're already used to, because we've been operating on things like maps and filters and with reduces and stuff like this. We've been passing functions to higher order functions like map, reduce, and filter, right? So the main difference between the RDD API and the DataFrames API was that when introduced, the DataFrames API was designed to accept just these Spark SQL expressions instead of arbitrary user-defined function literals like we used all over the place when we were learning about RDDs. And the reason for this was to give the optimizer a restricted set of operations that it already knew how to optimize based on. So these relational optimizations, it needed relational operations to do those relational optimizations, right? So here's a selection of some of the more often used methods, but we'll go into more detail in subsequent slides. But first, before I do that, I got to show you one important trick so you can actually see what you're doing with these relational operations. So to see what your data looks like. So there are a couple of methods in Spark to show what your data looks like. The first that I'm going to be using all the time is called show. It prints the data frame in a tabular form, and it shows only the first 20 elements. So it looks something like this. So if I have this employee data frame again, right, which we use 2DF on, and if I do show on it, it prints out this nice thing here, which shows all of the elements. In this case, there's only 4. Otherwise, it would show up to 20, but it prints these out nicely so you can visually sort of parse this easier. And then the other operation that we can use to get a look at our data is called print schema, which prints the schema of the data frame in tree format. So here's an example of what this looks like. I'm using the same exact data frame here, so this employee data frame that we saw earlier, and so here's what it looks like when we say print schema. So this is actually quite a simple schema. Basically, this is the root, and there's just one level of fields here. I have just 5 fields, one of type integer, string, string, integer, string, right? And all of them are nullable. Remember this nullable thing that we saw in previous slides. There's always this nullable Boolean that has to hang around to say whether or not one of these data types can be nulled out for some reason. Okay, so let's actually look at some of these transformations. 2 things to remember. We're talking about transformations right now, which means that transformations always return a data frame as a result. And second, don't forget that they're lazily evaluated. Okay, so just like regular RDDs, these are lazily evaluated too. Some of the most common transformations include select, which I'm sure you already have kind of an idea of what it might do. It selects a set of named columns, so more than one column potentially, and it returns a new data frame with these columns as a result. We saw this earlier when we said we wanted to select 2 out of the, 5 or several columns in the SQL query that we did in the previous session, where we took the employee's last name and the employee's ID number out of our data frame and returned a new data frame with those columns. So just visually, if you have a table with 4 columns and then you say I want to select columns A and D, then you get back a new data frame, or new table, I guess, with just these 2 columns. And you use select by passing the names of the columns to the select method. There are a few other overloaded versions of these. You can have a look at the Spark docs to see the different choices for selecting columns, but this is ultimately the idea here. The next transformation that's going to come up is called aggregate. So this one is peculiar, and we're going to go into more detail into it later in this session, but the short story is that aggregate performs aggregations on a series of columns, so on one or more columns, and it returns a new data frame with the calculated output, with the aggregated output. Okay, so we'll get more concrete about what that means a few slides from now, but moving on, group by, which you can kind of guess what that might do. So it groups the data frame using the specified columns. So it's important to note that this is a little bit of a weird method here. I say that it returns a data frame, but it doesn't exactly return a data frame, because this group by method is actually intended to be used right before an aggregation. So typically you would be doing a group by and then an aggregation after the group by. So we'll go into a little bit more depth when we talk about aggregations about what this group by exactly does, but you can think about it right now as grouping the data frame by some specified columns. Okay, and then we'll do an aggregation on it in a second step. And finally, one of the more commonly used operations is, of course, a join. There are many ways to interact with joins. We'll go into detail in the next session about all of the ways to use joins. Just remember that all of these things are transformations. Either they explicitly return a data frame or they indirectly return a data frame as a result. Of course, there are several more transformations, such as filter, limit, order by, where, as, sort, union, and drop. These are all basically the same operations that we know from SQL. All of these, along with their overloads, can be found in the Spark SQL docs. So I'd like to show you an example of how to use some of these transformations, but before I do, I have to talk a little bit about columns. So if we go back to the previous slide, we'll note that sometimes you pass strings to these operations, and sometimes you pass a column. And usually the strings are meant to refer to a column, but what's a column? So how do I actually talk about these columns in the context of these Spark SQL programs? So there's a few different ways to specify columns, and it can sometimes be confusing if you just jump into a code base without anybody telling you what these things mean. So the main three ways that you'll see people referring to specific columns in a data frame are as follows. Most commonly, you'll see this $sign notation, which is just a shorthand for specifying the name of a specific column. So if you're calling, for example, filter on some data frame, so I go to DataFrame.filter, and if I want to filter on the age column, I can do $, and then in quotations, put the name of the column, and then I can do whatever operation, whatever SQL operation I want to do. So this basically means the age column of this DF data frame here. So another way to refer to a specific column is to actually explicitly refer to the data frame. So we can, just like above, we can explicitly say, okay, the DF data frame here, and then the age column, we pass a string to it. So we pass age as a string, and then that's a signal to Spark SQL to look in this data frame for that column. And finally, the last way to do it is to use a SQL query string. So just like what we saw when we were actually writing out the SQL queries in this syntax like this, where the SQL query was a string here, Spark SQL actually parses that with a SQL parser and then figures out what are columns and what are operators from this string that you pass to it. So you can do the same thing here, where you can pass sort of a SQL query kind of and hope that Spark SQL can parse it correctly. There's sometimes some errors with this, so I would, if I were you, I would probably go with one of these two methods over this method, because these are a little bit less error prone. So now that we know how to refer to columns inside of these data frame operations, let's look at an example. Recall the example SQL query that we did in the previous session on this data set of employees. So we've been looking at this employee data frame now for a little while. Rather than using SQL syntax like we did in the last session, let's convert our example to use the DataFrame API. So if you remember what this example asked of us, it asked us to obtain just the IDs and the usernames of the employees working in a specific city. Say, in this case, we want to select just the people living in Sydney. Okay? And then let's sort the result in order of increasing employee ID afterwards. So once we've grabbed these columns and then filtered out the people who live in Sydney, then we sort them by the employee ID. So how would we solve this with the DataFrame API with some of the methods that you've seen so far? I'll let you try it first. The DataFrame solution actually looks a lot like the SQL query that we did in the previous session. In the previous session, we used a select statement followed by a where statement followed by an order by statement. We can do essentially the same thing here. So given the employee data frame, all we have to do is select the ID of the employee and the last name of the employee. So now we've selected those two columns, and then we filter out everybody who does not live in Sydney. And finally, we order the records or the rows by the ID. And as always, it's nice to try this out in a real data set. So this is the input data set, so this is what employee DF looks like. So in this case, we have these 4 records. And after running the Spark SQL expression here, what we get is a new data frame called Sydney Employees DF, like this, with only 2 columns, and then the ID numbers and last names of the people who live in Sydney, sorted by the ID numbers. So David Walker is now first, because he's 221. He lived in Sydney, so he's the first element, and then the next one is Slate Markham, who is now second because his ID is 645, and he also lives in Sydney, and the New York people are nowhere to be found. So here's an example of a few transformations on a data frame. Also, it's important to note that there are 2 methods available for filtering in Spark SQL. One is called filter, and one is called where. Both of them are the same. One is just an alias of the other, so you can always think of these things as completely equivalent. When filter looks better, write filter. When where looks better, write where. And also notes that it's possible to make filters a little bit more complex too. We can have Boolean expressions, ANDed or ORed, and we can also use several different columns in these expressions, so we can compare between columns as well. The only thing to note is that if you do a lot of this, it can be a little more difficult for the Spark SQL Query Optimizer Catalyst to optimize your queries. The last topic I'm going to cover in this session is grouping and aggregating on data frames. I mentioned kind of awkwardly earlier on that the aggregate method is meant to be used after a call to the group by method. Let me show you a little bit more what I mean here. So there's some special operations for grouping and aggregating, and this is because one of the most common things that you want to do with a table is to group data by some column, by some attribute, and then to do some kind of aggregation on that column or that attribute, like a count. So these things are a pretty common pattern. For grouping and aggregating, Spark SQL provides this group by function that I mentioned earlier, which returns this strange thing called a relational group dataset. This is when I said the type was simplified. We'll talk about that in a second. And then it has several standard aggregation functions defined on it. So these are defined on this relational group dataset, some of which include count, sum, max, min, and average, amongst many others. So you have kind of this two-step thing going on here. You've got to do group by, you get back this relational group dataset thing, and then you get some of these aggregation functions that you could potentially use. This can get a little hairy with the types, so the API docs are really your best friend here. But the basic pattern you have to remember is that you have some data frame, you do a group by on it, and then you call some other method like ag here, which I'll talk about in more detail in a moment, or count, things like this. So this count operation is defined on this relational group dataset thing, and it returns another data frame. So then you get back to data frames again. So this API basically requires you to go through two steps. First call group by, and then call some other operation to get you back to a data frame. This can look a little complicated, so let's look at an example to clear it up. So let's assume that we have a data set of homes currently for sale in one entire US state. Let's try to use these grouping and aggregating operations to calculate the most expensive and the least expensive homes for sale per zip code. So we want to do this per zip code. We want to find the most expensive and the least expensive per zip code in this entire state. So assuming that we have a data frame full of these listing things here, how could we compute these most expensive and least expensive homes for sale per zip code? I'm going to let you try it. Feel free to go back to the last slide if it helps, but see if you can use group by and some kind of aggregate function to do these calculations. Here's how we can do it. First things first, we're going to have to import another SQL import. So this one's called functions, and it gives you these things here, like the max and the count and all of that. So you're going to have to import that if you're going to want to use any of these grouping and aggregation functions. Otherwise, you just do group by zip code, which is pretty straightforward, right? We're grouping by the zip code, and then per each zip code, we want to know what the maximum price is of the listing. So the price is of type int, we can easily calculate the max, and we're grouping by the zip code, which is also an int, so now we have the maximum price per zip code, and likewise we can do the same thing with minimum, so we can just group by the zip code, so now we have groups of zip codes, and then we can choose the minimum one in each the minimum price in each zip code. This is extremely readable, extremely straightforward. If you want to see how this looks on real data, I encourage you to go to the Databricks Community Edition notebooks and to try this out on a real data set. You can almost exactly copy the code here. Okay, that was kind of easy, wasn't it? Let's try something a little harder. Let's assume that we have the following data set representing all of the posts in a busy open source community's discourse forums. So just think forums with subforums, okay? And we have this case class post here, which represents some activity or some post in this forum. Each post has an author ID, it has a location where this post was made. In this case, it was made in a specific subforum, and a number of likes for that post, as well as the date that it was posted. Now, assuming that we have a data frame full of these posts, let's say we'd like to tally up each author's posts per subforum, and then rank the authors with the most posts per subforum. Okay, so basically what we want to do is we want to count up all of the posts that people are making in each subforum, and then we want to basically figure out who was the person with the most posts in each subforum. So maybe we're going to give this person a community award or something, so we want to know who's the most busy in each one of these subforums, okay? How could we do this using these grouping and aggregating functions on DataFrames? I'll give you a few minutes to try it yourself. Okay, so first things first, we've got to import our SQL functions here. And after that, we just got to do a group by, an aggregate, and an order by. So let's step through this. So we want to group author IDs and subforums together because we're trying to figure out who's posted the most in each subforum. So we need both the author and also the subforums. And then we do an aggregation on these. In this case, I've used this interesting aggregate method, which itself takes another call to a function. I actually didn't need to use this here. I could have just used count, but I wanted to show you what it looks like to use it. And then I specify that I want to do a count on the author IDs. This gives me a new data frame with the following columns. I get an author ID column, a subform column, and then a count column. So the number of counts per that author ID in that subform, okay? And finally, I can just rearrange the order, and I use order by. So I have two parameters here because I want to first order by the subforms, and then I want to order by the counts. But notice I do this here, which says, okay, I don't want it to be in increasing order, I want it to be in descending order. So the count column will be in descending order, okay? So what does this look like on real data? This is maybe not the most beautiful data set that you're going to have a look at, but note that there are two subforms. They have actually similar looking names if you glance really quickly. One is called design, another is called debate. And let's just say I have three authors, author ID 1, 2, 3. Author ID 1 posts a lot in the design form, for example. And this is what the result of the group by aggregate followed by the order by looks like here. So as you can see, I've ordered by the subforms now. So I've got the debate subform first, followed by the design subform. And then I have the counts in decreasing order. So the author with the most posts in the debate forum is author number 2. And the author with the most posts in the design forum is author number 1. As you might have noticed, there's kind of two APIs here. There's this API that's available inside of this relational group dataset thing here, and there's also an API available for use with this aggregate method here. And each of these have individual Scala doc pages that you can look at to see what operations are available to you. So there's a set of operations available within this aggregate thing here, and you can figure out what all of those operations are by going to the Spark SQL functions page of the API docs. You can see a full list, and if you want to see a full list of the operations that you can call following a group by, have a look at the API docs for this relational group dataset thing here.